So you were unable to fix it?
That's why I switched from Windows 11 to Windows 10.
Okay.
Downloaded the Windows 1.
Okay, so it looks like I mean, so I'll be probably going back to my previous laptop to run the simulations. Yeah. Okay, so let me share the screen. So I apologize for the delay. I was in a classroom next to this one. I was talking to students in the IE 3360 class because I was inviting them to a meeting we have this afternoon. I'm also inviting you guys are here. So if you want to join us, it's gonna be at 5 p.m. It's for the IISC chapter. It's gonna be elections. People will be running for positions, leadership positions. So you are invited to come. So the other thing I wanted to discuss is the lab. So it looks like some of you are facing issues with the lab. So I got an email from you, Fantasher, and also I met with Saha. So in this lab, you have to remember the logic that you used to for the operators in one of the previous labs, in which the operator will go set up the machine. So you have to do the C's of the machine and the operator together. You do a C's delay of the machine and the operator together. And then you have to release the operator. The machine will process the part. And once the part is ready, you have to seize the operator again, perform the removal delay, and then release both the operator and the machine together. So I think that's the major challenge of the lab, to remember how to set up. In my conversation with Saha, he mentioned that we did that logic with all blocks, the elements and blocks. So he was curious in terms of how to use the current blocks to build the logic. So we discussed how to get that done. So in Arena for the new modules, there's also, if you go to advanced process, you will find a seize block, you'll find a release block. So that logic is there. So you can build a similar logic using those blocks. In addition to that, there's part of the logic, you have to make sure that you do the priority for the queue. So processing time for the machine, it will be a delay. Yes. But you have 3 delays in this logic. You have the delay for the setup, and that release, you seize the operator and the machine together, and then you delay both of them together. So you can use a process block for that logic. If you go to the process, seize delay, exactly, of both of them.
Then
release the operator, then delay, and then cease. Just the operator, just the operator. And then you do a delay release of both. Yes. Okay. Okay, so that's the other announcement or message is to remember that you have your project report due on Monday. So I wanted to get some feedback in terms of how's that going. So how's the data collection going?
Sometimes there are in my system there is but sometimes there is so much queue. Like there is something there no queue, then if one customer came and immediately he get the service or he get the cash.
And that's what time of the day?
12.
So at 12, she feel you're too type or Yes.
I think the business is not going well.
Okay. So I think that's.
I got the data, I think 116 data, 116 data, like, but I'm not sure whether it will be going.
Yeah, because remember that part of the exercise was to identify a time period in which you have a high demand. So there was a need for you needed to see a queue, right? Because then there's a bottleneck somewhere, and you're trying to use the simulation to fix that problem. Well, I mean, you need to, I mean, I will sit down and try to run the input analyzer right now with the data you have and see if you can get a good feed. If that's not the case, then you can go again. But I think you have more than enough. I mean, 116 data points. Yeah, that should be good.
More than 100 is okay, around 110.
So if you have more than 100 data points, you should be able, if you were consistent with the system observation in terms of the time of the day and the system, the amount of people that were in the system, the status of the system, then you should be okay.
So for me, what happened, like, I'm taking care of 12 p.m. The difference, like,
The business is going very good.
Tifel is going really well. Yeah.
every second there are 5%. So much hard to track it. So what I do, I started 10 people.
And you follow them.
But the arrival time is 5 times different. 10 people, 12 12 check. I'm tracking my 10 people. I have to check them.
See what you're saying? Yeah. So yeah, so I mean, I see that strategy can work. Like, for example, if you're just looking at getting data for, let's say, the inter-arrival time, so you can just focus on the inter-arrivals, right? And you say, okay, people are arriving every 30 seconds. And then you got, I don't know how many data points. And then you can just go and look at the processing time, right? And then once you get those two, then you have to go and get data about the actual performance of the system. So now you have to follow this person until he leaves or she leaves, because that's going to tell you this is the average cycle time. Mm-hmm.
Processing time also is better.
But you will imagine that in your system, processing time will be about the same. It's going to take them the same amount of time to get the food ready. Yeah, it's going to take about the same time to get the payment process. Yeah, so the other thing that is changing is the arrival rate, right? So between 12 to 12:10, you will get this many people arriving. 12:10 to 12:30, you have this many people arriving. So what we are doing right now, in terms of modeling, you can use that strategy to set up your arrivals, because they're gonna change according to the time period. What they are ordering.
Sometimes the customer who is coming into the system, but he gets the order early. Due to the less processing time, I think due to less processing time or due to the common order like this, sometimes the customer who came early, he got his food later.
Okay.
I also guess.
So it depends on the type of plate food they order, or how many meals they are ordering together.
Like if you order into the food, I think other than that, because it is the main food.
Okay.
It's kind of like outlier. Like out of 30 data, I have to see they're already more time.
Okay.
It's coming as an outlier.
Yes, I understand. So if it is something like out of the 100 observations, you see that only twice, then you don't necessarily have to account that as part of your system, okay? Because those are not typical observations. Okay, good. From the online audience, any questions, feedback? If not, then we can get started with the material for this afternoon. So we go back to our theory. And today we're going to be talking about push and pull production systems and the difference between them. And how are, I'm sorry, we have the screens. And how are they different? And what are the benefits of each one of them? And if there's a way for us to combine those two production systems into a one that will take advantage of the benefits of each one of them. So the agenda for this afternoon, we're going to talk about, we're going to provide an introduction, and then we're going to discuss the magic of pools. So what are the benefits in terms of reducing manufacturing costs, reducing variability, improving quality, maintaining flexibility, and facilitating work ahead. And then we are going to talk about a different concept also related to this production system that is called the Conweb. So what this stands for is the Conweb is a constant WIP. So we are basically running our production system by keeping a constant amount of WIP in the system, managing that amount, and making decisions based on that limitation that we are putting into the system. So for example, if we say the best amount of WIP that we can have in this manufacturing line throughout the day is 10, then we're going to be releasing jobs according to the amount of WIP that we have in the system. So if we get close to 10, then we're going to stop sending jobs into the production system. We are below 10, then we can continue sending jobs. And we'll see how that works. Also, we are going to do comparisons of this strategy with MRP. These are the typical production systems for push. So it's material production systems, and also we're going to compare that against Kanban, which is typical tool that is used for, or tools that are used for pull systems. So let's get started. Let's talk about the introduction. So in this lecture, we will provide a formal definition of push and pull systems at the conceptual level. So if you think about push and pull, yeah, you understand what the difference is. But then when we look at it as from a production system perspective, they're related, right? But they're managing your system based on a different philosophy. So we observe that most real world systems are actually hybrids or mixtures of push and pull. So in the philosophy is illustrated in this figure. So in the push system, we are basically producing as much as we can, and we store all this product, and we know that at some point that product is going to be sent to the customers, right? So we make as much as possible, we store it, and it has some benefits. So this production scale typically provides you with some savings. So if you need some parts, it's cheaper for you to buy a high amount of this number of parts than buying just a few of them. So it's this economic of scale alternative that you have available, and you're trying to exploit that particular benefit. So if you buy all these parts together, the cost per part will be really low. So you're using that as a to make a case that producing all these parts will save you money. However, if you don't move that product really quick, then you are incurring an additional cost for warehousing and so on. Pull is the opposite. Instead of making all you can as soon as possible, you're just producing when you need it. So if a customer is putting an order, then you tell your system, okay, this customer is asking for this many units. So let's put a signal into our system. So you produce those 10 boxes that are required. Then you start the production for that order, and then you send it to your customer. So the philosophies are different. In one of them, you're basically relying on some type of forecast. Say, I'm gonna need this many boxes for next month. So I'm gonna produce all of them now. And then when they're requested, I'm gonna send them from my warehouse. In the other one is just, okay, I'll wait for the customer to tell me what they need. And then I'm gonna start the production of that, and I'll send it to the customer.
Of the production system.
Yes.
They have like all the products before the order.
Yes.
And the other one, food system, I think,
You're waiting for the customer.
to order, then
Yeah, so you'll see the benefit of the push is that if the customer places an order, you already have everything on hand, so you can send that to the customer. You have a waiting time, right? So you will promise a delivery time, will take you a week, maybe. So, but you are going to deliver that when requested. So those are also, so each one of them will have benefits and disadvantages. So the key distinction between push and pull, I have a video here. So let's see. Good animation about the difference between this. So let's see if I can get the. Okay. So I guess because I'm using Zoom. Do you know how to play the share sound here?
It processes the quantity used for assembly, and likewise procure materials for the volume that has been processed. This.
No, it should have sound. The problem is that we are using the Zoom, and it will. I know there's a way for. Right here.
Let's look into the details of the
Okay, so
pull
it's not
system
working, so let's
production
see if I
style.
can
This
just
style is based on the
show you what's
orders
going on.
received. It assembles
here we
products
have
only
an
for the
order.
amount of order
This is the
received.
post-production
Then,
system.
it processes the quantity
So,
used for assembly,
as you can
and
see,
likewise procure
first
materials for the volume that has been processed.
Wait until we get an order.
This manufacturing
to
concept, which produces the right
set up
material at the right time at the
production
right
of
place
items.
and in the
So
exact
this time
amount,
is the
is called the
right material at the right
just-in-time.
time at the right place.
In the pull system production, a tool called Kanban is used to control the production. The
So,
Kanban representing the product that
typically
has
what
been
will
shipped
happen
or
is
parts used is handed from the post-process.
let's say a
The Kanban
card,
carries all the
they're telling
necessary
you,
information for production
we
and
need
logistics
this,
such as the part
many
number,
units.
pickup cycle,
In order
and
for us to
capacity.
get those units ready,
The
we
Kanban
have
provides
to,
instruction for production.
get started.
The production line will process
So
parts by
this
using
is
materials to
going to
fulfill the
trigger
instructions indicated
the
on the Kanban.
first process,
Once
which
the
is
parts have
putting
been
those
processed, The Kanban will be
units
attached and
that were
handed over to
in
the
the green box
post-process.
now into, after
Now,
producing them,
the Kanban of the materials used for
put it
processing will be
in it
passed
at
on to the
their
previous
beginning.
process to place
Same
an order.
time, that is creating a
In this
trigger
manner, a pull system
for
production
needing more
using the
parts.
Kanban is called the
So what's
Kanban
going to happen
production.
now, this is telling the
Now,
system,
let's
I need
find
more
out the flow
parts.
of the Kanban
So
production.
let's fill out that box.
Products are shipped based on
I
the
need to
orders
place
that
an
have
order
been
for
received.
those
The Kanban of
part
products that
materials.
have been shipped are
And
handed
the
down to the
process
previous
continues, right?
process in the
So
welding assembly
set
line.
up the car
Based on the information on the Kanban, parts required for assembly are picked up from the
the other
previous
processes
process and
that
assembly is
will
carried
need to
out.
trigger
In the
this box,
previous
so
processing
it
line,
will
the
trigger the
Kanban
other
of the parts which
processes,
has
and at the
just
same
been picked
time,
up now becomes an
everything is going to be
instruction order for
triggered after that.
processing. In the
So
processing
those
line,
cars are
materials
the ones that
required
we
for
call the
processing are
Kanban.
picked up from the
Kanbans
storage
are
and
going to be
then
used to
processing
keep
is
track
carried
of
out.
what's happening in the
The
floor.
Kanban which was attached to the
It's going to
materials will
trigger
be
all the
removed.
processes that are needed for you to
Based on the
complete.
information indicated on this
Why
Kanban
is
removed,
this
orders will
good?
be placed to supply
Your
materials.
inventory
Products that have been welded and assembled are
only
transferred to
have
the
in the
shipping area.
production floor what you need.
Materials that have been
You
ordered will
don't
be
have
delivered to the
excess of
factory with the
material, you don't
Kanban
have an
being
excess of
attached.
working process.
In this way, the Kanban is issued from the
So
post-process to the
what's going to
previous
trigger
process in order to
what's
pick up the
happening on the
parts
floor is
required.
the actual customer order.
Instruction for production is
Uh,
provided moving backwards of the processes. When products are shipped following the orders, the Kanban is issued to manufacture products. This means that if no products are shipped, no production instructions will be given. The Kanban enables to achieve the production concept of the right material.
It is already on the card.
This,
Yeah.
the colors,
Yeah.
colors are used to differentiate the steps of the process. So you see, there's also different colors for the boxes, and those are telling you, you know, I need this many items here, so I'm gonna take this card and I'm gonna place it here, or I'm gonna take the box and place it here. The card is gonna tell you how many units are needed. You complete the parts, then you move it forward. You know, for completing those parts, you need those items that were at the beginning of the production line. So now those, yeah, so those items are no longer there because you use them already. So that empty box is going to tell you, you know, this box is empty. Now you have to fill it with, and then that card is going to go backwards. You fill, and then to fill that box, you need to use other materials, and then the process is continuing. So the idea, again, you keep a low inventory, or you're just running the system with what you really need. Also, it creates some type of commitment from every employee, because they know these many parts are being observed by the next person right away after they're completed. So they're making sure that those parts are in good shape or is good quality. Because if they're not good quality, this going to notice right away. So that creates this level of commitment of quality that it is what makes Toyota really famous, right? Reliable cars, because they follow this process, and that process also created this high quality on the product that was make them different from, at least a few years ago, from other car makers. So that's the Kanban, and just in time.
Material at the right time at the right place and in the exact amount. In this way, the production speed can follow the sales speed. The main target of production control is to keep the inventory at its minimum by controlling the sales speed and production speed, and not to cause any stockouts.
So let's see, the
The sales speed depends on customers and competitors, therefore cannot be controlled by ourselves. This is why we have to change the production speed to control the inventory and stockout. However, the sales speed widely fluctuates compared to the production speed, which may create some moments in which the sales speed exceeds the production speed. So, we will have to accumulate the inventory when the sales speed drops. When the sales speed increases and the production speed cannot catch up, we will use the accumulated inventory. Having stock allows you to respond to the fluctuation of the sales speed. In a production schedule, we set the production amount to make sure that the volume of inventory and stock out on the demand forecast and production schedule. It maintains a certain amount of inventory and products are shipped from the stock every time an order is received. In this style, the key factor to minimize
So
example
this
of
is
a
the
production
difference.
line where
Let's
parts
look
are
at
processed
the
and
push
welded.
system.
The production schedule is
So the
planned
push
out based on the
system
demand forecast and internal information
works
from
differently.
customers.
We're gonna look at
Then, plans will be made for the materials, outsourced production, facilities,
many
personnel, production steps,
we
manpower,
are
and schedule.
thinking that we need these
Based on the
items,
production
so
schedule,
they're
the
gonna be
materials
producing
will be
for that
procured.
amount. So get all
Materials
the
are
parts
ordered in a large
together
lot in order to
in
keep the
front of the
purchasing
line,
price low.
and then they're gonna try
Then,
to
parts are
move those parts
processed using the
to every
delivered
single
materials
process.
and following the
So
production
you're
schedule.
creating this big
Processing lot is kept at a large
product,
size so that the frequency of
before
setups
you
will
have
be
the
kept at
ability to
minimum
look
to
at the
achieve
quality of the
inefficient
product, because
production.
you know there's some
Process parts are then
consistency
carried to the
in
assembly
the
area.
flow. But now
Parts are welded and
basically getting
assembled
this
in
many,
accordance with the production
maybe when you
schedule
get to
and
this
are
point, the
stocked in the
operator that
shipping
was in the
area.
station was no
The
longer there.
standard
You don't
stock
have
is maintained
a
to
clue
prevent
who
any
was in
stock
charge
out.
of doing what.
Just like the processing line,
So,
the main
but at the
target is
same
to
time
achieve
that you get these
inefficient
many
production by
parts
minimizing
together,
the assembly and setup
produced,
frequency.
and they're going to go
Products are
to
shipped from the stock
specific
following the
area,
orders
and they're going to be
received.
stored and
Now, let's
moved
sort out the logic of the push system production, which will
to
later be
the
compared with the
customer when
Kanban
needed.
production. The push system production is a production style that focuses on the logic of the manufacturer's side. The first point is the logic of procuring materials. Materials and parts are ordered at a massive lot volume in order to minimize the purchasing price.
For the manufacturing facility and the full system is just for the customer order.
Pull system, yes, triggered from the customer. Push system is triggered from a forecast of how many units you're going to be needing in the next time period. Yes. So this is going into what I mentioned already. The benefits of going into the push system is that if you order this many parts together, then they're going to cost you less. So you're taking advantage of this economy of scale, like what Walmart does. They buy very big lots and then they sell it in small price. So that's the idea. But then you have all the other components of having to hold these parts.
The monthly schedule is taken into account so that
for
all the
long
parts
periods
needed for the
if
month
they're
can
not
be
moved.
ordered at once.
What else?
Facilities and line systems
Mass
also focus on a
production,
big lot size so
high
that maximum
efficiency, so
efficiency
you
will
don't
be
have to perform
realized.
these many setups, right?
The third point is the
Like
logic of
if you're just
inventory.
producing these many parts and then moving to another product family, it will take you some time to do the setups, and then you have these associated delays, making changes and so on. Whereas if you're producing, let's say, 1,000 parts in the same run, then this mass production will give you that high efficiency, right? You're making all these parts together. And the inventory, the myth of this safety stock, meaning that you have enough in a warehouse in case the customer places an order, you already have enough to supply the customer. So you never this safety stock myth is basically saying you never let your inventory to go below a certain number, right? So you always keep a certain amount of products in store in case you are needing them fast. So if you think about what happened with COVID, I think most of the products that were needed for, let's say, safety for the doctors and the nurses, the masks, everything, when there was a high demand, there was not enough products in inventory. The reason why is most of the companies are moving to these high efficiency methods in which you keep low inventories, you save money by not running these big warehouses, but that would not be good in all scenarios. That's what I'm trying to say. So if you know of public safety products, other type of products that are needed by people, then you shouldn't think about those products from a cost saving perspective or a efficiency perspective. You should think about those products from a need perspective. So you always have enough in store in case you need them in emergencies. So
The basic idea is to have a large amount of stock to feel secure that there will be no and industries with less demand volume will exceed demand forecast. Also
yes,
implement a style that is
post
flexible to
the video. I mean, it's part
fluctuations.
of the slides. So
To
if you
achieve
want to
this
look at
style,
it,
the manufacturing
by
speed must
yourself,
follow the
you can
sales
do that.
speed, which reflects the actual
Unfortunately,
demand
that we
trend.
couldn't
It is a method.
play it here with the volume. I think people in the online, they're able to listen to it, but anyway, so unless, yeah, I think our speakers were, no, I'm using the speakers for the mic. Something has to be with what we are doing. Anyway, so the key distinction between push and pull, after watching the video, we can at least understand the differences from this picture. We're trying to illustrate the same concept. So we have the push and pull mechanics. So for push, we have a schedule we have to follow. So we're going to be sending those units into the production process in order to make that many units that are forecasted to be needed. So for those type of production systems, you'll see that there's an unlimited web, unlimited working process. You saw that in the video. You have all these big lots that are created, these pallets of products, and those are being moved throughout the production process. Whereas in the pool system, since this is but it's not infinity. It's not infinite. It's unlimited in the sense that you are not putting a top or control on the amount of web that you will have in the floor. So it would depend on how many units you put into the production system. So let's say you're producing 10,000 parts. So if you're waiting for those parts to be completed in order to move them to the next process, then the amount of web that is staying in the system is high.
10,000 parts at the first one station. There will be every part will be going from like 10,000 part will go from station 1. Then it will be going to station 2 unless the 10,000 part is going from the station 1. Like it will the first station 1 will work through every part from the 10,000 part. Then it will go into the station 2, or it will be like go one by one. Like,
yeah, those are good questions. So I think we discussed the differences between the advantages and disadvantages of between having a large batch and individual batches in terms of movement between the facility. So it will depend. But what this trying to, it will depend on whether you are moving every part, single part at the same time, or moving a group of parts together to the next station. You have processes in which you wait until you create this palette of product before you move them. Or you have processes that would just take, I mean, you will bring all these parts to the first station and then you will move them individually to the next station.
So if I move the parts individually, and there will be like not there will be some.
Well, it's going to be, it doesn't matter, because if you're moving 10,000 parts individually or moving 10,000 parts together, there's still 10,000 parts in the process, right? Right. So what this unlimited means is that you're not putting a ceiling on your web. Sometimes it could be high, sometimes it could be low, but there's no ceiling on the web. Whereas in the pool, since you're putting these cards and they're telling you exactly how many items you need, you always have a limited web into your system, and you can track that amount based on the cards that are placed into the system. So if you have an order, let's say of 10 units, 100 units, you will know that the web will not exceed that amount, because you have placed an order for that amount, so your web will never go above that amount. So that's the difference. Push system schedule work releases on the basis of information from outside the system, while pull system authorize release based on the information from inside the system. So a pull system establishes a priority limit on the working process, what the push system does not. And that's what we are trying to differentiate here. So what is the magic of pull? So there's a limit on the maximum amount of inventory in the system. So again, you're gonna know how many units are being processed because you're keeping track of it. All pull systems ensure that no matter what happened on the plant floor, the WIP level cannot exceed the pre-specified limit, which is based on the amount of parts or orders that are being placed. By establishing a WIP cap, pull systems play a very strong emphasis on material flows. So if we know if production stops, then the input will stop. You are not gonna keep pushing parts, right? If a machine fails in the pull system, then you know that you're not gonna be able to send the car to the next station. So the production will stop. Whereas in the push system, if you have a failure of a machine and you already started the process, you will have all these parts waiting for that machine to be fixed in order to continue the process. So in a pull system, if the production stops, machine stops, then you know that the input, you will not continue having all this flow of inputs into the system, it will stop. So reducing manufacturing costs, if the WIP is capped, then the disruptions in the line, such as machine failures, shutdowns due to quality problems, slowdowns due to production mix changes, do not cause the WIP to grow beyond a predetermined level, which is what we are trying to explain, right? So you have all these parts in the push system, all these parts are getting ready to get started, right, in the production. So let's say you have 3 machines and the machine that fails is the last one. So in the push system, you're going to continue processing those parts until they get to the queue in front of machine 3. So that would put, or will not, you will not have a signal to stop the production unless you have a person telling you, no, wait. But if, let's say you have these on separate departments or you have these on separate rooms, if you don't have a way to see what's going on in the other room, then you will continue putting these parts into the first 2 processes. So the WIP will grow. And if you have multiple lines that are depending on this station, you have all these parts coming into the system and waiting for that machine to get fixed, then you'll have all these big WIP waiting for to be produced or continue the production using that last station. So the WIP, on the contrary, if you look at the WIP system, you have these cards that are going to tell you, you know, machine 3 is not working, so we cannot, I'm not going to be needing materials from you until we fix this machine. Once we fix the machine, we can continue complete this process. And now I'm going to be able to put the signal for you to come to fill out this box. So that's the difference. Reducing variability. The key to keeping customer service high is a predictable flow through the line. In particular, we need low cycle time variability. Okay, so so if you put an order as a customer, and I tell you as a production manager, I tell you, okay, I'm gonna have that order for you in 7 days, right? So you need to make sure that your cycle time inside the production system is lower than 7 days so you can deliver that to the customer. So we saw that in the first couple of lectures, the importance of handling the variability, because if you know that you have a high variability in your system, then making sure that you deliver these products on time is going to be very challenging, because you don't know if you have high variability process, you don't know exactly how long is it going to take you for you to complete these parts. So The key to keeping customer service high is to make sure that you are able to predict the flow that you have in your system. So if you have a very reliable system, a very reliable process, then you should be able to estimate, okay, this is going to take me this much, and then I can promise this lead time to my customer. So low cycle time variability. If cycle time variability is low, then we know with a high degree of precision how long it will take the job to get through the plant. Okay, so if my process is reliable, low variability, I have a better control of knowing when my products are going to be ready. This allows us to quote accurate due dates to customers and also meet them. So reducing variability, we spent several weeks on talking about this subject to see how that's important now. If you put together a good process, reliable process, then you'll be able to have a good quality of service for your customers. So reducing variability, I think this is something that we show with a problem in class. Suppose that a one-card Kanban system is in use, which limits the width between machines to 5 jobs. So in this example, we have 2 machines, the one on the left and the one on the right. And machine 1 is the first one in the process, then machine 2 is the second one in the process. So everything that is processed in machine 1 then is moved to machine 2. And we have a Kanban system that is in use, which is limiting the width between machines to 5 jobs. Okay, so I'm gonna put, we have the production cards for machine 2 here. We complete the parts with cards entering outbound the stop point. And once we complete these parts, we put the cards here, and then those are gonna authorize the start of the work of the previous station. So when stock is removed, place production card in the hold. So suppose that machine 1 is subject to periodic failures. So we have the first machine, and this machine is subject to some failures. So we had 2 machines. Machine 1 feeds machine number 2. The machines are these circles in blue now. Machine 1 is extremely fast, producing parts at a rate of 1 per second, while machine 2 is slow, producing at a rate of 1 per hour. And we know that we have a Kanban system that is going to limit the working process between the machines to 5 jobs. Because machine 1 is so fast, this buffer will be virtually always be full whenever machine 1 is running. So basically what this is saying is we're always going to have parts ready when needed by machine 2, right? So we are just going to move them when they are needed to the next station. However, if a failure lasts longer than 5 hours, then machine 2, the bottleneck right now, which takes longer, will start. Okay, so even though this machine is really fast, if you have these periodic failures, if those last longer than 5 hours, then machine 2, the bottleneck right now, will start. Thus, depending on the frequency and duration of the failures of machine 1, machine 2 could be start a significant fraction of time, despite the tremendous speed of machine 1. Okay, so this is something that we discuss in terms of failure and the length of the failures and the frequency of the failures. So what this is trying to illustrate is that even though you have a process that is really fast or a machine that is really fast, if you don't control the variability of these failures and the duration of these failures, you can still, even though machine 2 is the bottleneck, it can start because you have a high variability in terms of the failures happening in machine 1. So reducing variability is important. That's the message. Improving quality. Workers from downstream workstation must go to an upstream workstation to get the parts. So this is what I was referring to with the commitment to quality, right? Because now I'm an operator. I need to go get some parts from the station in the line, the station before mine. So I'll go there and I would, before I move them to my station, I'll make sure that these parts are in good shape or at high quality. So if the parts are not acceptable, the worker can reject them immediately. Okay, they're not want to take the blame, right, of the next station down the road. They want to make sure that when they get there, they're good quality, they do a good job. When they pass them to the next station, the next person is not going to complain. So that commitment to quality, because I know someone is going to come and going to make a judgment on my work, improve the quality of your product. The result will be a quicker detection of problem and less likelihood of moving and working on bad parts. If you think about the push process, you have all these parts going into each machine, so you have a large amount of them. There's no way for you to inspect all these parts once they get into your station, right? So you have this mountain of parts. It's impossible for you to go check all of them. But if you have this limited width, you know that you're getting these parts from the station. You want to make sure that those parts are good before you move them to your station. Maintaining flexibility, that's another advantage of pool. By preventing release of parts when the factory is congested, pool system keep orders on paper as long as possible. So this will facilitate engineering and priority scheduling changes. So what this is saying is, since you are not putting orders into the system right away, like you are waiting for, let's say you have these orders, you're waiting for them to be complete to put the next one. You're not putting them in a queue saying that, okay, this order will go next, this order will go next, this order will go next. You're waiting for the system to complete to put the next order. The factory is not congested, and you have the opportunity to make scheduling changes. So let's say you got an order, a high importance order, an order that you have to complete right away. You have the flexibility of changing the schedules based on the current status of your system. Also, releasing work as late as possible will ensure that releases are based on firm customer orders to the greatest extent possible. The net effect will be an increased ability to provide responsive customer service. So all these things are relevant and make this pool system very efficient, and also in terms of quality of product and savings in your production systems, make them very a good system. So now we are going to transition to this Conweb concept, and what this is trying to do is somehow taking into consideration, or is taking into account, the benefits of both push and pull systems, and it's trying to combine them into a single system. And let me illustrate that. So Conweb stands for constant work in process. This is protocol under which a new job is introduced to the line each time a job departs, right? So in push systems, you're just pushing parts into the system based on a forecast or based on the orders that you need to complete. But you're not releasing these orders by taking into account what is the current status of the system. You're just pushing these orders into the system based on schedule. In pull systems is the opposite, right? You're putting these orders into the system, and you are just producing based on the orders. But what the Conweb is trying to do is and you are going to be pushing parts into the system, but you're also keeping track of the amount of whip that you have in your system. And if you go above that amount, then we're going to stop the process until you complete that. So the idea is to maintain this constant whip, and that will take advantage of the low inventory in the production line. And it works well under certain scenarios, but that's the idea. You keep track of the whip, and you're just releasing, introducing to the line each time a job departs. So this assumes two things. The production line consists of a single routing along which all parts flow. So a single routing means that these parts will go through these stations all the time. And the jobs are identical, so the whip can be reasonably measured in units. So if you see here what's going on, you have a parts buffer at the beginning of each station. So the circles are representing the stations. And these are moved to the next station based on the amounts that are the current amounts of these buffers. So we remove the production car and attach to a complete part. Right, so these parts they have the cars attached, meaning that they are completed, and you put them into the buffer. So as soon as the part is completed, right? So then you have space in the buffer, so you can complete another part. Same thing here, you complete another part. So this results in a whip level that is very nearly constant. So departing jobs send production cars back to the beginning of the line to authorize the release of new jobs. So this is what's saying here. Once you have the finished goods, you put that car back at the beginning of the line, and you can start the process again. If the facility contains multiple routings that share some workstations, or if different jobs require substantially different amounts of processing on the machines, then things are not so simple. So this figure are illustrating the differences between Conweb push and pull. So these lines, dotted lines, are representing the authorization signals, and these are representing pull containers. So as you can see, at the top we have the Conweb, in which you're putting a signal every time you have your last part completed, or the last station as a completed part. You put in a signal at the beginning of the process. In the push, you have the signal at the beginning, so you're pushing those parts through the system. And the pull, you're putting these signals on every station. So to analyze Conweb lines and make comparisons with push systems, it is useful to have a quantitative model of closed Conweb systems. Similar to the Kingsman's equation model we developed for open push systems in the variability basics lecture. So we are going to use the following notation to describe an end station Conweb line. So we have here the notation. Uj is the utilization of station J in Conweb line with whip level W. So that W in parentheses is representing the whip level. So I don't want you to get confused. Before I think we were using that to illustrate the machine number, right? Now that parenthesis is containing the whip level. CTJW is the cycle time of station J in Conweb line with whip level W. CTW without the J is going to be equal to the summation of all CTJs for W. And then throughput W is the throughput of Conweb line with width level W. WIPJ W is the average width level at station J in Conweb line with width level W. So let's look at the mean value analysis model. So what this does is represented here by these equations. So we let WIPJ 0 being equal to 0 and the throughput 0 equal to 0. So basically what this means is if you have a width of 0, this WIPJ is going to be equal to 0, or the Conweb line with width equal to 0, and the throughput is going to start with 0. This mean value analysis model or algorithm computes the cycle time, throughput, and station by station width levels as a function of the number of jobs in the Conweb line in iterative fashion by using the following. Okay, so we have this CTJW equation that is taking into account the effective production or processing time, the square coefficient of variation of the effective processing time, and also the throughput levels and the working process levels. So you see here, we have, for example, TE square. In parentheses, you have the J. J is the number of the machine. For CTJW, in parentheses, we have the width level. And then we have CTW. Again, we defined this already as the summation of all the cycle times for all CTJs, Ws. The throughput for W is going to be the width level divided by CTW, and WIPJ is going to be equal to the throughput times the cycle time. So these formulas are easily implemented in a spreadsheet. So these are more iterative formulas, right? So you're going to compute, let's say, for W1, and then once you get W1, you can get W2, and so on. So, and we can also generate these curves of throughput and cycle time for Conweb line other than the best, worst, and practical worst case. So let's illustrate the use of equations 10.1 through 10.4 using the penny fab example. If you remember the penny fab, we have 4 stations, each with an average processing time of T equals 2 hours. And we consider the penny fab with reduced variability so that the coefficient of variation is equal to 0.5. And starting with WIPJ equal to 0 is going to be equal to 0. We can compute the following. So using WIPJ 0 and throughput 0, we can find the cycle time for the line when the working process is equal to 1. Okay, so what we are doing here is we are taking this equation 10.1 and we are substituting the values for throughput W minus 1. Since we are finding CTJ for 1, W is going to be equal to 1. So when we set up throughput W minus 1, that's going to be throughput 1 minus 1, so that's equal to 0. But we know that we are going to assume that at 0, this value is going to be equal to 0. So we can find the value for CTJ1, and that's going to be equal to 2 after substituting out these numbers. For j equals 1 up to 4, since all stations are identical, CTW is going to be equal to 4 times CTJW, and therefore CT of 1 or width 1 is equal to 8 hours. So the cycle time for W equals 1 is going to be 8 hours. And we found out that's the case, right? You have one part is going 4 stations, each one is going to take them 2 hours. So it's 2 plus 2 plus 2 plus 2 is going to be equal to 8. The throughput is going to be 1 over, which is the WIP equal 1, divided by the cycle time of 1 is going to be 1 over 8. And the average WIP at this station is going to be WIPJ for 1, which is equal to the throughput of 1 times the cycle time J of 1, which is 1/8 times 2 is 1/4. CTJ, J is the machine. So this will be the cycle time of machine, one machine. Yes, machine 1, machine 2, machine. So there's 4 machines. Yes. So total cycle time will be the summation for all machines. Yes. Having computed this for W1, we next move to W2, right? So we can use the values that we found for CT1, WIP1, and throughput 1, and we can substitute that into this equation for 2. So that's what I meant by an iterative process. So you find the values for 1, and now you can use those values for computing 2. You find the 2s, then you find the values of 3. You find the 3s, now you find the values of 4, and so on. So following the same process, we now get the cycle time J for each machine equals 2.313. So the cycle time of 2 is going to be 4 times CTJ, which is going to be 9.25. And the throughput is going to be 2 over cycle time 2, which is 0.216. Continuing this in this fashion, we can generate the numbers shown in table 10.1 chart here. So depending on the WIP level, we can obtain these MBA calculations for penny fab with the C equals to 0.5. So as you can see, the throughput will increase as we, the cycle time is increasing as we increase the WIP. Cycle time in each station is also increasing. Throughput will also increase, but it will not increase as much as the amounts that we are observing for cycle times. WIP for each station is also increasing. So using the same, we'll also generate THW and CTW for the case in which we increase capacity, for instance, by reducing the average processing time at stations 1 and 2 from 2 hours to 1 hour. We have done this and plotted the results for both the reduced variability case from table 10.1 and the increased capacity case, along with the best, worst, and practical worst cases in figure, in this figure. So this is the resulting. So we have the practical worst case, the best case. We also the increased capacity and the reduced variability. So notice that both cases represent improvement over the practical worst case. So the reduced variability and the increased capacity, both of them are better than the practical worst case, since they enable the line to generate greater throughput for a given WIP level. In this example, speeding up 2 of the stations produce a greater improvement than reducing the variability on all stations. Now that we have models on both push and pull system, we can make some comparisons to deepen our understanding of the potential benefits of pull systems. So we begin by comparing Conweb with MRP and then construct Conweb with Kanban. So MRP is for push, Kanban is for pull systems. So for push systems, fundamental distinctions between push and pull systems is the following. Push systems control throughput and observe the WIP. Pull system control WIP and observe the throughput. So for example, in push system, we establish a master production schedule, which determines planning orders releases. These in turn determine what is released into the system. Depending on what happens in the line, however, the working process level may float up and down over time. So this is what we discussed. So we establish this production schedule. We know we're going to send these units into the system, and then working process will go up and down depending on the status of the system. In a pull system, the working process level is directly controlled by setting the card counts. However, depending on what happened in the line, the output rate may vary over time. So things that can happen are faders, machines, and so on. Which approach is better? Well, this is not a simple question. We can make some observations. So working process is directly observable, while throughput is not. Hence, setting working process as a control in a pull system is comparatively simple. We can physically count jobs on the shop floor and maintain compliance with the WIP cap. In contrast, setting the release rate in a push system must be done with respect to capacity. Since WIP is robust and observable, while throughput is sensitive and can be controlled only relative to the observable parameter of capacity, this is a powerful argument in favor of pull systems. Efficiency, a second argument in favor of pull system is that they are more efficient than push systems. By more efficient, we mean that the WIP level required to achieve a given throughput is lower in a pull system than in a push system. So we have this law for Conweb efficiency. For a given level of throughput, a push system will have more WIP on average than an equivalent Conweb system. So we are comparing now the Conweb versus the push. So what this is saying is the throughput, a push system will have more WIP on average than equivalent Conweb system. And for a given level of throughput, a push system will have longer average cycle time than an equivalent Conweb system. Okay, so in terms of Conweb versus push systems, it shows that given a level of throughput, the Conweb system will be more efficient in terms of producing in lower cycle times. Now, if we compare Conweb versus pull systems, both systems establish a WIP cap. They exhibit similar performance advantages related to MRP or push systems. Specifically, both Conweb and Canva will achieve a target throughput level since less WIP than a pure push system, and it will exhibit less cycle time variability. So both of them have these advantages. The card count issues, the most obvious difference in the Kanban requires setting more parameters than does in Conweb. So you need more cards in the pull system than in a Conweb, because in the Conweb you only have one signal happening from the end to the front. So in Conweb system, there's only a single card count set. Since coming up with appropriate card count requires a combination of analysis and continual adjustment, this fact means that Conweb is intrinsically easier to control. But remember, this Conweb methodology only works under certain assumptions. So you have a line in which all products will go through the same line. You're working with the same type of product. The routing is the same. If that's not the case, then the Conweb will be difficult to manage. Product mix issues, the experts from Kanban were clearly aware that it will not work in all production environments. Conweb, while still requiring a relatively steady volume, is much more robust to swing in product mix. It's a result of the planning capacity introduced by the process of generating a release list. Oops. So that's the last slide. And that will complete the lecture for today. So we talk about push and pull systems, and we compare those, and we also compare those two systems against Conweb. Any questions? Good. So I think there's an assignment. So you can look at that, and next time we can discuss. If you have questions, if not, then we'll continue our discussion on Monday. And let me know if you have any questions.